back again to our Ask IITians. Again, a very lengthy topic but a very interesting topic. So you people are going to enjoy today's topic because today I'll be telling you something about how are you going to calculate the pH of different types of solutions. And let me assure you very nicely, if you understand the topic today, you're going to rock in the exam because these types of questions are generally asked in all the competitive exams. So let's begin with today's class where I'll be telling you how are we going to calculate the pH of the solutions. Let's now start up with another topic where we are going to discuss about the pH calculation of the different types of solutions. So what we are going to do in the pH calculation for the different types of solutions, I'll say that you can have the solutions of different types. For example, I can have a solution of two different acids. I can also have a solution of two different bases. I can have a solution of a strong acid and a strong base, a strong acid and a weak base, a weak acid and another weak acid, and there can be hundreds types of solutions which are there. And now what we have to consider is what are the pH of the solutions of different types of these solutions which will be starting. So let's first of all consider the pH of a mixture of two strong acids. So let me say I have two strong acids and I am mixing those two strong acids, and now I have to determine what will be the pH of the resulting solution. If I say that if V1 volume of a strong acid solution of normality N1 is mixed with V2 volume of another strong acid solution of normality N2, then we can say that, let us for example consider we have a strong acid HX1 and we have another strong acid, let us say for example HX2. So I can say that this 2 is not what we meant by the second, there will be 2x. Rather than writing it this, I'll say, let us say there is a strong acid HX and there is a strong acid HY. So this is our acid number 1 and this is our acid number 2. Since both of these are strong acids, so I can say HX get dissociated to form H positive plus X minus. Similarly, HY gets dissociated to form H positive plus Y minus. And it has been given to me that let's say HX has the normality N1 and the volume V1, and HY we are taking of normality N2 and the volume will be V2. That means what will be the total number of H positive, the total equivalence of H positive that will be given by the acid HX will be nothing but N1 V1. So I have N1 V1 as a number of moles of H positive which are contributed because of HX. Similarly, if I take the concept of HY, I'll say N2 V2 will be the total number of moles of H positive which will be contributed from the acid HY. Now, he says that we can say the number of H positive which are coming from solution 1 will be N1 V1 and the number of H positive which will be coming from solution 2 will be N2 V2. And if I am saying that the final volume of the solution will be nothing but V1 plus V2, because I am taking V1 volume of first solution HX and I am taking V2 volume of second solution of HY. So if I take into account, let us say what will be the normality of the resulting solution, I can say that the normality of resulting solution will be nothing but N1 V1 plus N2 V2 by V1 plus V2, and this will give out the term N which will be found as the concentration of resulting solution. And if I am talking about the concentration of resulting solution, that means I can say that the concentration of H positive in my new solution will be nothing but N1 V1 plus N2 V2 by V1 plus V2. If I take this thing into account, I can now find out what will be the pH of the solution will be nothing but minus log of the new concentration of H positive which is there. So taking the value from the above equation, I'll put the value in this equation pH is equal to minus log of H positive, and hence I'll be able to calculate what will be the pH of such a solution of two strong acids. And this was the first case that we have discussed. So here we can look out the fact that H positive concentration will be given by N1 V1 plus N2 V2 by V1 plus V2. Now knowing the H positive value, you can very easily calculate what will be the pH of the resulting solution. Let's now move over to another example where we will consider some other kind of solution. Let us say we are considering a mixture of two strong bases. So if I am considering a mixture of two strong bases, I will consider the same way round. If I have one HYOH and the another as HOX. So it's going to give me OH minus and Y positive. Here it is going to give me OH minus plus X positive. So we can very easily find out if N1 V1, so if N1 normal HOY solution of volume V1 is mixed with another HOX solution volume V2 and the normality N2, we can very easily find what will be the total concentration of OH minus. It's nothing but we will multiply the total number of moles of OH minus from both the cases. So we'll say the total number of moles of OH minus from both the solutions, and then I'll divide this value by the total volume of solution. So here I'll be able to find what is the concentration of OH minus. Now if I know the concentration of OH minus, I can use this formula H positive into OH minus is nothing but 10 to the power minus 14. This value is known to me, this value is known to me, so I can very easily find what will be the concentration of H positive. If I know the concentration of H positive, I can use the formula pH is equal to minus log of H positive, and it will be very easy for me to find what will be the pH of the resulting solution, which is made up of two strong bases. Now considering the second case also, let's talk about some further details of what will be the mixture of a strong acid and a strong base. Now let's say for example I have considered a mixture where I have added one strong acid into another strong base. So if I consider so, I'll say that the acid-base neutralization reactions will take place. Because a strong acid is going to contribute H positive, a strong base is going to contribute OH minus, and hence this H positive and OH minus will combine with each other to form water. That means a kind of neutralization reaction will be taking place. Moreover, I can say that the solution will be either acidic or it will be basic, but it depends on which of the component is taken in axis. Now to prove this point of whatever we have just stated above, that any solution of a mixture of a strong acid and a strong base, it can either be acidic or basic in nature, whereas it depends upon which component is taken in axis. So to prove this point, let us consider if I say if volume V1 of a strong acid solution of normality N1, that means the number of moles of H positive given to me will be N1 V1. Now if this is mixed with the volume V2 of a strong basic solution of normality N2, that means the OH minus, number of moles of OH minus given to me is N2 V2. Now if the two are being mixed, so I can say the number of H positive in solution 1 is N1 V1, the number of OH minus in the given solution is N2 V2. But the total volume of solution is nothing but V1 plus V2, because I am mixing V1 volume of first solution and V2 volume of second solution. Now there can be two different cases. Either the value N1 V1 will be found to be greater than the value N2 V2, or the value N2 V2 will be found to be greater than the value N1 V1. Now N1 V1 is the number of moles of H positive. That means here the concentration of H positive or the number of moles of H positive is found to be greater than the number of moles of OH minus, and in this case the number of moles of OH minus is found to be greater than the number of moles of H positive. If this is the case, I will say the N2 V2 moles of OH minus will be reacting with N2 V2 moles of H positive. So the left out amount of H positive will be nothing but N1 V1 minus N2 V2, and this will be divided by the total volume of solution. So I'll be able to calculate what is the total concentration of H positive in such a solution. And since I am saying this solution has more amount of H positive than OH minus, so the solution will be acidic in nature. Now if the solution is acidic in nature, I can very easily find the pH as minus log of H positive concentration, and I'll say that the pH will be found to have a value of less than 7. Let's now consider the other way round, when the concentration of OH minus is found to be greater than the concentration of H positive. So if I am saying N2V2 is greater than N1V1, that means N1V1 number of moles of H positive will be first of all neutralized by N1V1 number of moles of OH minus. So the left out amount of OH minus will be nothing but N2V2 minus N1V1. So these are the total number of moles of OH minus available in the solution. If I divide it with the total volume, so I'll say this will be the concentration of OH minus in the solution. If this is the concentration, I can use the formula H positive into OH minus gives the value as 10 to the power minus 14. You put the value here, you know this value, so I can easily calculate the concentration of H positive. Now knowing the concentration of H positive, I can calculate what will be the pH of solution. And since such a solution has more amount of OH minus as compared to the H positive, so I can say that the solution will be basic and hence the pH value will be greater than 7. So this was the case which we had considered about the pH of a mixture of a strong acid and a strong basic solution. Let's now move ahead where we'll be talking about the pH of a weak acid, which is a monoprotic acid solution. So how are we going to discuss in this case? I am saying we have to consider the pH of a weak acid. If I am talking about a weak acid, let us say I am talking about HA. If it's a weak acid, it will get dissociated to form H positive plus A minus. And he says that if I am talking about a monoprotic acid, that means it contains just one proton, and this is what we have considered as an example. So he says that the weak acid doesn't get dissociated 100%. So we have to actually put into consideration the percentage dissociation of the weak acid that we can do using the Ka, which is nothing but the dissociation constant of any acid. And hence, since we are talking about a weak acidic solution, that means we can use here the Oswald's dilution law. And if we use the Oswald's dilution law, I can say that let me consider the concentration of the weak acid which I am considering here is C. So at time t is equal to 0, let us say the concentration of weak acid is C and there is no H positive and no A minus present in the solution. Now with due time the HA starts dissociating and it forms H positive and A minus. So I can say that at T is equal to T equilibrium, let's say alpha is the degree of dissociation of the weak acid. If alpha is the degree of dissociation of weak acid, so I can say if I am taking C as the concentration of HA, so we will say C alpha gets dissociated. If C alpha gets dissociated, I'll say the remaining amount will be C minus C alpha. H positive will be C alpha, A minus will be C alpha. So I can say that Ka will be nothing but concentration of H positive A minus by concentration of HA. If I substitute the values here, I can say it will be C alpha into C alpha by C 1 minus alpha. So I can say again that it is C alpha square by 1 minus alpha. Now, if we say alpha is very less as compared to 1 because it's a very weak acid, so I can neglect this alpha in comparison to 1. If I neglect the alpha in comparison to 1, I'll write Ka is equal to C alpha square. So I can say alpha is equal to root Ka over C. Now to find the pH, what do we need? We just need the concentration of H positive. The H positive concentration is given to be C alpha. If I replace the value of alpha, I'll say C times Ka over C. So if I take the C in the square root, I'll get Ka into C square over C, which is nothing but Ka into C. So now in the question, you will be given the value of Ka, you will be given the value of C, so you will be able to calculate the value of H positive. On calculation of value of H positive, you will also be able to calculate the value of pH of a solution, which is minus log of H positive. Thus, Using this method, we can very easily calculate what will be the pH of a weak acid, which is a monoprotic acidic solution. Let's continue the discussion further, and let's talk now about the pH of a mixture of a weak acid, which is a monoprotic acid, and a strong acidic solution. Now, if I am talking about a weak acid and a strong acid, I can say that both the weak acid and the strong acid will be contributing H positive to the solution, because a strong acid will always get dissociated to H positive. And also a weak acid can also get dissociated to H positive. So for the first approximation, we can neglect the H positive ions which will be coming from a weak acidic solution, because always we say that if you have a strong acidic solution, the amount of H positive which will be contributed in the solution by the strong acid is going to be far more greater than the amount of H positive which will be contributed by the weak acid. So on a first approximation, you can almost neglect the concentration of H positive given by a weak acid. And thus you can simply calculate the pH of the solution from the concentration of a strong acid only. But if we are asked to calculate the exact pH, then we'll have to take the effect of the presence of strong acid on the dissociation equilibrium of a weak acid. To consider this point in details, I will say that suppose you have a strong acid HA. Now if it is a strong acid, I can say that this gets dissociated to form H positive plus A minus. Since this is a strong acid, so I can always write this H positive plus A minus. Now if I consider a weak acid, let us say HB. Now since this is a weak acid, I can say that this will always be existing in equilibrium between H positive and B minus. So let me say that let the concentration of strong acid be considered as C1 and the concentration of weak acid be considered as C2. So if we take into account this equilibrium which I have written, let us say HB is getting dissociated to form H positive and B minus. If this is so I'll say C2 is there, and at time t is equal to 0, the concentration of HB is C2, whereas the concentration of H positive is 0 and B minus is also 0. And at time t is equal to t equilibrium, if I say alpha amount of C2 gets dissociated, so I'll say the concentration will be C2 minus C2 alpha. Here I'll have C2 alpha and here I'll have C2 alpha. But what we have to take into account is that there is an equilibrium which has been established for a weak electrolyte. Now to this equilibrium of weak electrolyte, we are adding a strong electrolyte which is having one ion in common. So if it is having one ion in common, I can say that because of the addition of, this will be C1 concentration of H positive which is now there with us. So we can say because of the addition of a common ion to the already existing equilibrium solution of a weak electrolyte, there will be some differences in the dissociation constant of the weak electrolyte. And hence we can also say that now for this weak electrolyte HB, I will write the K2 for this weak electrolyte. I can say this will be concentration of H positive, concentration of B minus divided by concentration of HB. Now instead of writing the concentration of H positive as simply C2 alpha, I will write it as C2 alpha plus C1, which will be multiplied by C2 alpha and which is to be divided by C2 minus C2 alpha. So if I take something as common, I can very easily say that this value is nothing but C1 plus C2 alpha into C2 alpha by C2 1 minus alpha. If I write this thing, I can say that this is C1 plus C2 alpha into alpha by 1 minus alpha. Now whenever we have to find out what is the concentration of H positive in the solution, since we are going to find what is the pH of the solution, I can say that the alpha value is very less than 1. Although the electrolyte Hb was a weak electrolyte, so alpha value was already less than 1. But now, on the addition of a strong electrolyte, the degree of dissociation further decreases. And if it further decreases, the alpha value is found to be very, very less. So, if it's very, very less, you can neglect this value of alpha, and hence the value of Ka2 will be written as C1 plus C2 alpha, which is times C2. Now, you know what is the concentration of C1, you know what is the concentration of C2. So, I can very easily find what will be the value of Ka and alpha. So, I can say the concentration of H positive ion now will be given as C2 alpha plus C1. Now, if we know the value of K2, we will be able to find the value of alpha. On finding the value of alpha, I can replace this alpha in the concentration of H positive. Now, knowing the value of H positive, I can find the pH very easily as minus log of H positive, and hence I will be able to calculate the pH of a mixture of a weak acid and a strong acid. The weak acid taken in this case is a weak monoprotic acid. So, this was how we calculated the pH of such a mixture. Now, let's move ahead to find out how we can calculate the pH of some other different solution. So, moving ahead, we want to calculate the pH of a mixture of two weak acids. So, now I have to take into account two weak acids. So, both the two weak acids which I am taking into account are monoprotic acids. So, let's say first weak acid which I am considering is Ha1. The other weak acid which I am considering again to be monoprotic is Ha2. And we are now mixing these two weak acids, and we have to find out what is the pH of the mixture. So, we say both the acids will dissociate partially because both these acids are weak acids, and we have to take into account the concentration of H positive which is given from the weak acid 1 as well as the concentration of H positive which is given by the weak acid 2. So, let's say the acids are Ha1 and Ha2, and the concentrations we are taken to be C1 and C2 respectively. Let us say alpha 1 is degree of dissociation for first weak acid and alpha 2 will be the degree of dissociation for the second weak acid. So, I can say this will follow the order H positive plus A minus, A1 minus, and this is going to follow the order H positive plus A2 minus. Let's consider both these two acids one by one, and let's try to find out what is the concentration of H positive given by the respective acid. So, if I write this thing for the first acid Ha1, it will follow the equilibrium H positive plus A minus. So, if I am saying that at time t is equal to 0, the concentration of Ha1 is C1. So, I will say this is 0, this is 0. Now, at time t is equal to T equilibrium, I can say if alpha 1 is the degree of dissociation of this weak acid Ha1, so the amount of H positive will be C alpha 1, the amount of A1 minus will be C1 alpha 1, here also C1 alpha 1, and here the left out amount of Ha1 will be C1 minus C1 alpha 1. That is fine. Now, let's move ahead for the second acid which is given to us. Let's say the second acid given to us is Ha2, and it is going to form H positive and A2 minus. If this is the case, and if I am saying C2 is the concentration of the acid which is given to us, so at time t is equal to 0, the concentration of H positive is 0 and that of A2 minus is 0. So, at time t is equal to T equilibrium, I will say let alpha 2 is the degree of dissociation of the weak electrolyte Ha2. So, here I will write C2 minus C2 alpha, here I will write C2 alpha, and here also I will write C2 alpha 2, because this is the second degree of dissociation which we are considering for the another acid. But now, we should know that both these equilibriums are taking place in the same container. This is because I have already put Ha1 in one container and I am putting Ha2 also in the same container. So, that means the concentration of H positive in the container cannot have two different values. So, if I am saying that the concentration of H positive in the container cannot have two different values, so this means this is the wrong concentration and the correct concentration will be C1 alpha 1 plus C2 alpha 2. Because here we have to consider, we have to take into account the total number of H positive which are coming from both. And here also I should consider C1 alpha 1 plus C2 alpha 2. Now let's apply the equilibrium constant law here. So according to which I can say Ka1 will be C1 alpha 1 plus C2 alpha 2 multiplied by C1 alpha 1 to be divided by C1 1 minus alpha 1. And if I solve it out, I will say that it is nothing but C1 alpha 1 plus C2 alpha 2 into alpha 1 by C1. 1 minus alpha 1, and C1 got cancelled. And if I do the similar way for the acid HA2, I can write Ka2 will be C1 alpha 1 plus C2 alpha 2 multiplied by C2 alpha 2 to be divided by C2 1 minus alpha 2. If I deduct this term, I can say the value will be C1 alpha 1 plus C2 alpha 2 into alpha 2 by 1 minus alpha 2. Now what do we have to take into consideration is we need to find what is the pH of solution. To find the pH of solution, we should keep in mind that pH is minus log of H positive. So if anyhow or the other I am able to find this value C1 alpha 1 plus C2 alpha 2, I will be able to find the total concentration of H positive. I can put it up in the above equation and I will be able to find what will be the pH of solution. To consider such a case, what we want to do is I can represent this C1 alpha 1 plus C2 alpha 2 terms as Ka1 by alpha 1 is nothing but C1 alpha 1 plus C2 alpha 2. So similarly, I can represent here also in the terms of Ka2 as by alpha 2 as C1 alpha 1 plus C2 alpha 2. So anyhow or the other, if I am able to represent the concentration of H positive as C1 alpha 1 plus C2 alpha 2, I will be able to calculate what will be the pH of solution. Now using the approximations, it has been found that the concentration of H positive for such solutions will be represented as under root of Ka1 into C1 plus Ka2 into C2. Now in any particular question, you will be given the value of Ka1, you will be given the value of C1, you will be given the value of Ka2, you will be given the value of C2. Hence, it will be easy for us to find what is the value of H positive. Now knowing the value of H positive, we can very easily find what will be the pH of the resulting solution. So this was a case where we had considered the pH of a mixture of two weak acids which were both monoprotic acid. So considering all the approximations, if anyhow or the other, will be finding the pH as C1 into Ka1 plus C2 into Ka2. So I will be able to find what is the total concentration of H positive. Now using the formula pH is equal to minus log of H positive, I can say minus log of C1 Ka1 plus C2 Ka2 raised to the power 1 by 2. I will get the value as, so minus log m raised to the power n is minus 1 by 2 log C1 Ka1 plus C2 Ka2. We will use this formula to find the pH of such a kind of solution. Students, so in today's class we all discuss about what were the different ways we are going to calculate the pH of different solutions. I hope today's class will be very much helpful to you people. But what I want from you once again is to go back, and this time once you go back, please concentrate on good questions, because if you try doing the questions, you are going to get more confident for your exam. So now in the next class, we will be discussing about the relative strengths of acids and bases. That's an easier topic, so you are going to enjoy once again in the next class. By the time, take care and do well in your lives.